Good. All right, welcome everyone to this seminar on this beautiful Wednesday evening or Thursday morning, depending on where you are. We are excited to hear from Dr. Brian Gelder as he speaks to us with some of his work. I'm going to start the seminar by doing the land acknowledgement. Iowa State University aspires to be the best land grant university at creating a welcoming and inclusive environment where diverse individuals can succeed and thrive. As a land grant institution, we are committed to the caretaking of this land and would like to begin this event by acknowledging those who have previously taken care of the land on which we gather. Before this site became Iowa State University, it was the ancestral lands and territory of the Bakoje or Iowa Nation. The United States obtained this land from the Meskwaki and Sauk nations in the Treaty of 1842. We wish to recognize our obligations to this land and to the people who took care of it, as well as the 17,000 native people who live in Iowa today. So we are going to hear from Brian Gelder, but who is Brian Gelder? Dr. Brian Gelder is a research manager in the Department of Ag and Biosystems Engineering. He has a bachelor's degree in agronomy and agricultural and biosystems engineering from ISU, a master's degree in bioresource engineering from Colorado State University. He got his PhD in soil science and agricultural engineering from ISU in 2007. He is an adjunct professor in the Community and Regional Planning Department, Ag and Biosystems Engineering Department, and Agronomy Department here at ISU. He co-leads a team that operates the Daily Erosion Project and also develops applications for the USDA Agricultural Conservation Planning Framework. Some of the courses he teaches here at ISU are GIS programming and automation and fundamentals of remote sensing and spatial analysis. On this note, we are excited to hear from you, Dr. Brian Gelder. The floor is all yours.
Thank you, thank you. I guess probably should, so first I want to, well, maybe a disclaimer. If anybody has any problems with what I'm hearing, Rick Cruz taught me most everything I know. So blame Rick Cruz if So, kidding aside, I want to take a little bit of time to recognize my co-author on this work. And he did actually a lot of this work, Forrest Williams. You may know Forrest Williams from his time here at Iowa State University as a master's student with Peter Moore over in NREM, where he did some stream migration work. And now he's defending his PhD from Massey University in New Zealand. He spent the last few years quarantined in a fairly safe location down in New Zealand. So, but yeah, otherwise I want to thank a few other DEP people: Rick, Daryl Hersman, David James, Claudette Sandoval Green, Tim Sklenar, Kelly Nascimento, Thompson, anybody who's worked on the Daily Erosion Project, thank you. Don't want to do the full rundown of everybody, but thank you all.
Brian, if you wouldn't mind hitting the more, and then I think you
Then
could produce
it'll disappear again. I don't know. So all of a sudden it made itself bigger in the middle of the.
Hide meeting controls.
Okay, press escape to show floating meeting controls. Okay, escape is my safety button. All right. So first, we're going to do a little introduction to the Daily Erosion Project. Might want to say why are we doing this? What does this even mean in the first place? Talk a little bit about depth management database, and then the new DEP management database, and what we're doing to try and figure out residue cover across the state of Iowa. Things not working. All right, we'll try the buttons. All right. So what is the Daily Erosion Project? It's a daily soil erosion estimator for the, well, not just for the state of Iowa anymore. We do most of Nebraska, most of Minnesota, and good chunks of Nebraska, Kansas, and Missouri right now. What we do is we generate estimates of soil erosion at the Huck 12 watershed level every day, precip runoff, sheet and rill erosion, and net detachment over those time periods. So we're primarily looking at, fairly small watersheds, and we're actually looking at about 125 watersheds in each one of these locations. So it's got a lot of high resolution geospatial, georeferenced inputs that form our data layers, and then we query them. I'll talk a little bit about what those data layers are right now. So we've kind of got primary four different data layers that come in there. We bring in NextRad precipitation, some LiDAR elevation data for the terrain and elevation analysis. We use the gridded Sergo product to get some soil properties. And then we use field scale land use and management database from the Ag Conservation Planning Framework that allows us to figure out what's going on kind of at the field level across these watersheds. And so the Ag Conservation Planning Framework shares this as part of their conservation planning, and it also works very well as inputs to the Daily Erosion Project. So we bring all that together into our WEP erosion model. So it's a kind of a flow path or hill slope based erosion model, and we get estimates of the growing crops and the amount of runoff and sediment that's lost while those crops are growing in the field and being harvested and being tilled. So what's our first input? We bring in weather, currently using pretty much about the highest resolution rainfall data you can get, 2-minute 1 by 1 kilometer rainfall product. And then we bring in some lower resolution, other climate or other weather data, wind, temperature, and solar radiation to figure out, how good the conditions are and how fast these crops should be growing. Daryl Hersman's our wizard behind most of getting the Daily Erosion Project up on the web, and he's got a lot of his code up there. And this pretty much every day starts about 1:30 in the morning, and then about 3-4 hours later, he's processed a few 100,000 model runs and generates our web page. I'll show you at the end of the presentation. We process a lot of elevation data for this project. We have to make water flow across the land surface. We've got lots of problems. Terraces that we need to work through, road embankments we need to work through, water and sediment control basins. But we've got to also keep these things in mind because the hill slopes don't go all the way down, all the way through these things. Those hill slopes respect those barriers, terraces, and the water's typically not flowing over those as long as those terraces are in good repair. Wasp cobs as well. So we have to keep track of elevation from a couple different standpoints, one from a completely flowing watershed standpoint and one from a partially flowing standpoint for our data sets. Then we bring in one of the other data sets is our land use and management data set. And these are primarily derived from pre-2008 common land units from the USDA. Back in the day, we used to be able to get the polygons directly from the USDA, and then in 2008 Farm Bill, they says no more. And so if you got the old stuff, you can work with that, and then we manually edit that. Claudette Sandoval Green and her team of students edits those to reflect certain crop data layer years. And so Iowa's data set currently is pretty old. They're working on updating it. It's one of the original ones, currently 2009 basis. And then this is what's available as these Ag Conservation Planning Framework field boundaries. How does this start to come together when you start stacking all these data sets together? We can get general maps of land uses, and we've got general land use categories in the ACPF. And then we've also got our Sergo data here. And on this you can actually see some of the subcatchment boundaries that we use to break Huck 12s into smaller smaller units. And then within that, we randomly place flow paths for water to flow. And what we're modeling here is essentially the yellow portion of these hill slopes. So we start at a flow initiation cell and model that down until we think concentrated flow, really starts to become the dominant erosion process. And it's not so much the more random rill action or sheet action that occurs higher in the landscape. And so that's more, that concentrated flow is more in the black portion of this hill slope here. So we're primarily modeling the yellow going into the black areas. How do we break that? How do we model those yellow areas? So we break that up into multiple flow elements in the WEP erosion model. We break those at land use and soils boundaries. And then we get slope estimated at each OFE from the elevation model that we're processing. And so we get both length, and we get an length along that flow path and the elevation along that flow path. So what do we have being estimated? Here we've got, hopefully an understandable graphic that kind of shows you. We're primarily looking at the upper portions of these hill slopes, and you can start to see concentration of flow occurring down at the lower portions of these hill slopes, where we're going to continue, where after every tillage practice, we'll get gullies forming in the same location. And so that's the black areas down here. That's where you're going to have ephemeral gullies forming. So how does that work out? We're doing Huck 12 estimates of these processes, and that's going to be based on multiple subcatchments, a few hundred subcatchments in there. We find we like to have around 100 subcatchments to get a reliable estimator of the erosion in that area. Most of the time there are more subcatchments, so we don't sample and run every subcatchment in there. And then our flow paths are just randomly located within our subcatchment based on flow initiation cells. So probably the interesting thing I'm hoping to talk to you about today is the DEP management layer. This is essentially a map of residue cover. And what we do is we try and remotely sense this residue cover from both Landsat and Sentinel-2 sensors. So we're looking at differences here in the shortwave infrared portion of the spectrum, where you can see, these are out beyond the visible and the near infrared portions of the spectrum. Those are here on the left side of this, where we start to see some differences, especially if you look at, if you're using hyperspectral data, these things are very easy to pick out. These changes in reflectance from residue and soil are very easy to pick out. Problem is we don't have good wall-to-wall coverage with hyperspectral sensors to cover the globe. So we work with Landsat and Sentinel-2 data because it's got decent abilities in these areas, at least has some abilities in these areas. Data's free, and Sentinel or Landsat, you're getting data about every 8 potentials every 8 days, and Sentinel about Sentinel-2 about every 5 days for capability. So looking for data that will actually give us information on what's going on. You lose things to cloud coverage and other things like that as well, but those are things we're working with. And you can see from our analysis, those are the problems we have to deal with working with the optical data. So this research started with an Iowa Nutrient Research Center funded residue cover data collection project in 2015 to 2017. So thank you, INRC, for this. And it's taken a while to get the analysis done, but we're pretty happy with where things are finally ending up on this project. So it's about 251 locations we had sampled over those years on both private farmland and Iowa state farmland. So what are we trying to determine for the Daily Erosion Project? So Daily Erosion Project, being an erosion model, the easiest way ag engineers have figured out to say these things is tell us what tillage systems you're using. So most erosion models they could use residue cover as a pretty good predictor of soil erosion, but that's not typically information people have. You don't have, most of the farmers can tell you, I use this tillage practice. They don't know how much residue cover is being left behind at various times of the year. So we have 6 different mulch levels or management practices in the Daily Erosion Project, going from our depth 1 to depth 6 number, varying from a very low intensity, a no-till system, to a very high intensity fall moldboard plow system. And this is essentially, on the right-hand side is the residue cover we expect under those systems at planting time. So our no-till systems are typically expecting in Iowa soybeans to have about 25% residue cover, and the soybeans to have about 73% residue cover. Silage, other small grains, sorghum having different levels as well. Then you can see down here a little bit lower what exactly each one of these systems entails for the depth management or for the wet management practices. So how did we gather this data? We went out and did some field campaigns, collected multiple locations per field, typically around 5 locations per field, to try and avoid biasing our estimates too much. We moved to we moved 30 meters away every time, trying to cover getting to multiple Landsat pixels with this. And then we had students do some grid overlays and do some data counts. And when we worked with this, we actually eventually buffered our field boundaries in 30 meters to try and reduce some edge effects. So this is some examples of what type of imagery we were coming back from the field with. Weren't always able to get out there before planting, but within a week or 2 of planting, so we could still actually observe what the residue cover conditions were. When we see vegetation in there, we remove that from our counts. If there's living vegetation in there, we don't count that as either soil or residue. We just move on and using our grid system and move to the next point and evaluate that. Well, here's our distribution of our residue cover samples. You can see we don't have great coverage across the state of Iowa, limited a little bit in our geographic locations, but pretty well sampled in north central Iowa. I had a lot of contacts, family contacts and friend contacts up in that area. Prairie City, Iowa areas where we see another location, Ames, Iowa, the Southeast Research Farm, and the number of farmers down there we had made some contacts with. Got some samples out at the Armstrong Farm and down at McNay, other locations as well. So one of the things that is fairly interesting and still new at least in the residue cover area is the use of Google Earth Engine in our analysis. Where Google Earth Engine's been around for a few years, many years, for about 7 or 8 years now, but it's still gaining traction in the use in the remote sensing platform. So we did a lot of our data management locally. So in this, oftentimes you do a lot of initial data management locally, and then we move to Google Earth Engine just because it's a great platform if you're trying to do remote sensing analysis across more than one image. If you're trying to look more than one image date, use Google Earth Engine, please. It's going to save you a lot of pain. No longer. When we started this project, we had literally tens of thousands of Landsat images on hard drives over in Ag and Biosystem over in my office that we had to do our own data management on ourselves. When USGS updates things, you need to go get all that data all over again. Google Earth Engine does all this for you, saves you tons of time. Especially, I had an assistant who was pretty much tasked with a lot of, doing that for 10, 20 hours a week, keeping that data up to speed. And it runs a lot faster than what we could do before. So how do we kind of divide that? Mostly, figuring out our survey data and our field polygons was done locally. Then we did most of our working on, moving clouds, calculating our indexes, I'll talk a little bit about, and then summarizing these time series by pixels and then polygons was all done on Google Earth Engine. And then we moved back to our local machines for a little bit, doing our regression analysis and our tabular data management. So can't speak enough about good stuff about Google Earth Engine. There is Microsoft has a planetary computer, I think, that's in beta as well. It's probably going to have, similar abilities. Don't want Google to get all the credit for doing all the cool stuff. So there are multiple options. There are becoming multiple options for doing these kind of projects out there. So we looked at a number of different indexes, some residue cover indexes, primarily used the normalized difference tillage index for residue cover, which is shortwave infrared 1 and 2. So in that little bit longer part of the infrared spectrum that I was talking about earlier. Then we used a vegetative index, so normal near infrared and red ratioing, normalized difference ratio for ascertaining how much green vegetation there was, and then we would threshold. One of the things we did was thresholding the images and saying, if these fields are getting too green, we're not going to use them in our analysis. So once the crops are too vigorously growing, we'll remove them from our analysis. We also had a moisture index, normalized difference moisture index from the near infrared and shortwave infrared 1 that allowed us to remove some of our overly wet soils. So what did that allow us to do? With those different indexes, we could calculate. One of the things we needed to do was calculate some thresholds. How high on the NDVI scale is too high? How high on the NDMI scale is too high? What values do we want to look? What values do we want to remove? And so we looked at, essentially removing from the fields, removing, up to by 10% bins, removing 50, 60, keeping 50%, 60%, 78%, 80%, and 90% of the image. So, throwing away potentially 10% because it's too high, 20%, 30%, and then looking at what those values are. And so on the right, we've got an image showing kind of how these indexes vary throughout the year. So we've got our day of year down at the bottom. You can see tillage index, is pretty consistent across from values are pretty consistent March, April, May, and then it starts rising in June. And tillage index, despite its name, is affected by vegetation. It's not as strongly affected by vegetation as NDVI. Well, it's actually more strongly impacted than NDVI, but it's more responsive to that residue cover signal than the vegetative index is. So here we've got farmers tilling their fields, kind of keeping things fairly consistent on the tillage index overall, and then it really starts to increase as vegetation increases in later parts of the year. Same thing with NDVI. See a little bit different trend. Very low at the early spring, about now, and then increasing a little bit. So you're getting a little more green matter out in those fields up until about early to mid-April. Then it stays pretty level while farmers are actually out doing tillage, maintaining fairly low levels of vegetation, and then it starts to take off. Once the corn crops and soybean crops start emerging. Our moisture index, I don't have quite as much explanation for what's going on here, other than, it seems our soils are drying out. We get snow impacts, rain impacts. Solar radiation is increasing through this time period, so it's going to dry things out a little bit faster. And then we start seeing an increase again up in the June, mid-June. And I'm not quite sure what's going on with that portion of that index, but that's what we see. So it hasn't been well researched what to do. How do you determine what levels to use? So we played around with those threshold quantiles to say how much data should we throw away? What's going to give us the best regressions? And so, as you can probably guess, our accuracy is best when you kind of throw away a lot of the data. The really green The really wet pixels, you actually get, we actually get our best accuracies, for at least from an R-squared standpoint, and from somewhat a mean absolute error standpoint. R-squared better high, mean absolute error better low. At our lowest, throwing away the most data. But the problem is, if you use a 60% threshold, where we've got very good R-squareds, pretty good mean absolute errors, we can only cover about 60%, 60 to 65% of the cropland and get enough images. Because what we're looking here is we are looking for, I should have said this, we're looking for a minimum value on that tillage index. Because we're kind of saying this tillage index responds strongly to the residue cover. And we want enough coverage to be fairly certain that we've gotten that minimum value. So we're looking for minimums in that response. So every time we get an image for each field, we get a tillage index value for that day. As farmers till their fields, they're going to have lower and lower amounts of residue cover, and that's going to result in a lower NDTI. Problem is, and then I said, once vegetation starts growing, that actually brings your tillage index up again, because tillage index responds to vegetation as well. So you're kind of looking for that sweet spot where you've gotten a good number of images. You're pretty certain you've captured the minimum value for that field, but you don't want to throw away too many images. And because of that, we kind of look at where we've kind of settled upon 80% as our optimum. Because at 80, if we're using an 80% threshold, so we're throwing away about 20% of the data being too green or too wet, we get about 86% coverage of our data. So every year you're going to have estimates for about 85% of your corn or soybean fields that way. You might lose some every one. You're not going to get an estimate for every field every year this way, but you're going to get one, 8 out of 10 years, 9 out of 10 years, somewhere around that, which we think is a pretty good compromise between accuracy and data coverage. So one of the problems we'll see in just a little bit, when you do best fit regressions, just minimizing your R-squared, what happens is you often overestimate the low end residue cover. So if we did a best fit, maximum R-squared on here, we would get an intercept, the tillage index would intercept 0 at about 20% residue cover. So the tillage index, this is a normalized difference tillage index. So 0 is not the minimum, but typically that's where it's actually pretty close to that value where you see 0% residue cover, but it varies by soil. And so that's one thing we're going to we'll talk about at the end. But when we used the best fit R-squared, it was very difficult to find anything that wasn't, pretty much in that mulch till or higher residue cover category. So with that maximum R-squared. Soil erosion action is where we've got low amounts of residue cover. So if we just use that, best fit R-squared, we were overestimating residue cover, and that's what we're concerned about when we're looking at residue cover, or when we're trying to estimate soil erosion. So we're using the approach where we anchor our intercept using our 3 lowest residue cover values in the training data set to try and improve our low end soil erosion estimation. So this results in a lower R-squared and mean absolute error, but it does allow us to estimate or what we feel are more accurate estimates overall, especially in the Des Moines. So here you can see our differences between our normal and our anchored regressions. So our normal best fit R-squared, we're a little higher on it. If at NDTI 0, we're at about 20% residue cover. NDTI practically ends up, minimums are about 0.05 for really black soils. Lighter colored soils are a little higher. And that's what, that's kind of the benefit of that. We lose some accuracy in the R squared though. We can see our anchored R squareds are going down compared to our normal, our best fit R squareds. And the thresholding you can see, so this is using our optimum threshold. This is our no threshold data. So I kind of outlined some of the bigger outliers that our thresholding removes from this process. So you can see it's removing a good number of our ones that have the poorest performance. And we think it's pretty reasonable to remove a lot of these, especially ones that have high NDVI, because we know those fields are pretty green. There's a lot of vegetation on the ground, which is corrupting that NDTI, the tillage index value we're trying to look at. So we're very happy that we're very confident, removing these outliers is justified. So probably the most interesting stuff, what does this look like when you get actual residue cover predictions for the state of Iowa? Here we've got a map of the median residue cover for 2011 to 2021. So an 11-year median of the residue cover on a pixel level basis for the state of Iowa. I kind of show you the MLRA boundaries on there, and you can definitely tell where the Des Moines lobe is. We definitely see much lower residue covers in the Des Moines lobe, but it's good because driving around the state of Iowa, I know we also have our lowest residue covers, and it jives with with my experience in our set and our training data sets. We started looking at this at an MLRA level. On our left-hand graph here, we don't have, I'm trying to remember the MLRAs right here. I know this is the Mississippi Valley soils. Can't remember what this one is in far northwest Iowa, but we're neglecting those because we have so little residue amount of those MLRAs in the state. They aren't included on the left hand here, but you can see the trends in residue cover for the state of Iowa for that same time period. Color coding, we bottom out at 20%, so don't think the Des Moines lobe is at 0% residue cover here, but it is substantially lower residue cover at planting in the Des Moines lobe than it is in most of the rest of the areas. And you also see the same trend, similar trend in that our three MLRAs that are the lowest, are below the statewide mean of residue cover are pretty much our three northernmost MLRAs. They're also, by far our poorest drained MLRA. And the other ones are also our other northern ones as well. So some things from soil management. Cooler, the further north you get, probably the worse your soils warm up, the more you want to till, especially when you've got lots of closed depressions in there. One thing, we were starting to, this is fairly new still, but we're starting to try and figure out some more explanatory variables, or at least some correlations between what's going on here. You also, if you plotted corn price and soybean price on here, we definitely had our highest corn and soybean prices back in 2012, 2011, 2012, 2013. Very high corn prices. I think that's, showing a reason that we had a lot of our lowest residue covers at that point. People doing more tillage for preparing corn seed bed versus soybean seed beds. Typically, you'll see a lot more no-till or reduced tillage on soybean ground than you will corn ground. If you look at and then if you also look at the NASS planted acres across this time frame, we're up in the actually low 14 million acres for corn in this, in the 2012 time frame, and now we're just slightly, 2011 was 12.9 million acres. So we had about 10% more corn ground and a corresponding 10% decrease in soybean ground in the 2011, 2012 area when corn prices were going through the roof. Soybean prices were good. They got to keep up with corn to try and buy some acres. But corn acres were really going gangbusters back in that time frame. Corn prices again are going gangbusters. I don't know, so I don't know what this is going to mean for the future. But Dad's talking to my dad today, and he's saying spot market at the co-op right now is 702. You had it's like, dang, I sold. So you always sold too soon, but $6 still is not bad corn price. But it's over $7 now. I kind of expect to see this trend reverse a little bit. Maybe in the next year or two, again, we might start seeing lower residue cover levels across the state. One thing also to notice in here is our MLRAs. You might notice. Sure, we've got 3 MLRAs down here, and we've got 1, 2, 3, 4, 5 MLRAs above the mean. Part of the reason that mean is still so biased down towards these is if you look at our residue cover map. So this is this residue cover map is only generated in areas that had corn or soybeans at some time between 2011 and 2021. We don't generate residue cover estimates typically don't do it on pasture land, grassland. We use the cropland data layer to filter out those areas. And okay. So that will explain a little bit. We have more acres in these are fairly large MLRAs, and we've got a lot of acres in these. So that's kind of pulling our statewide mean down more than you might expect from the number of MLRAs. So some things that if we zoom in at a higher resolution, anybody who's familiar, who's taken Dr. Burris's class where they go up and look at the old Lake Cairo mud lake in central Hamilton County, about 30 miles north of Ames. That old lake bottom is Renee Dietzel used to be in the department. Their farm is just on the north edge of their Lost Lake farm. Is just on the north edge of this lake here, of this old glacial lake here, tiled out about 100 years ago. So for a general idea of where we're at, we've got a lot of depressional land. The Gelder farm is right up in this area, and so I've got a lot of farmers I work with up this area when I've done my sampling. You can see definite biases in our products still, even after we haven't done any soil specific calibrations for this model, but you can see definite soil trends. The depressional soils, we have a very large depressional soil area here, that's low lying. Similarly here, and the lake bottom isn't quite, it's not actually quite as depressional looking as you'd think, but it is still more so than a lot of the surrounding areas. We've got some small depressions in our ground here showing up as very low residue cover. Most of these fields, and here, most of these, you can kind of pick them out by their general outlines. They should be a little more uniform than they are because these farmers are using consistent tillage practices across the entire field. And what we're seeing is a little bit of the differences in soil background reflectance instead of residue cover levels, because we don't have any good way to control for that soil variation at this point. But very interesting. Generally, these numbers are pretty reasonable. I know I did a lot of the tillage practices on this farm during this time period, and a 10, 20%, 30% residue cover level was pretty common for what we were doing that time frame. Those low depressions actually get down into somewhere 0% residue cover. That does happen in a few times because you'll get depressional ponding, you'll get ponding in the depressions and all the residue floats to one side. So you do get a few years of zero, but typically it's not as much zero as it actually shows up on these images. Another example map for, here's Ames, and we've got Nevada area, Colo. So we got Highway 30 heading east out of town here. And we've got, similar patterns that we're seeing. We get some areas somewhat correspond to some of the moraines in the state, or vary with the moraine terrain. You don't get as much of the depressions in those areas. So we see some, definitely soils based trends. Then we see, we got a farmer down here who's doing, I'm guessing, a good bit of cover cropping. You get very definitely no-till and probably actually a little bit of cover cropping to get some very high residue cover numbers down in this area south of Colo. So start seeing some interesting things. I may go talk to that guy and see if I can get some residue cover samples off of his farm at some point. So where are we going right now? One of the things we're working on is analyzing these changes in DEP management codes over time. So the last time I did this was an image by image analysis, pretty much around 2010 for the Daily Erosion Project. And I'd like to see how these depth management codes have varied over time. We also know we're starting to see some geographic MLRA differences in residue cover. Might be useful to help if these things are driven by some policy differences, maybe it's useful to understand what's going on in these different areas, or is it purely soil management choices by the farmers in that area? And are there things that we can do to help change those patterns to reduce some soil erosion? We also want to investigate some additional methods for tuning these residue cover algorithms to soil specific reflectance. There's been a couple research papers on this, but nobody's found anything that works well yet. We've got some additional ideas from this product that we'd like to investigate in some future research and go into that as well. And one of these things we haven't actually plotted out, we've got our statewide mean residue cover, but we haven't broken this out by corn and soybeans for these areas as well. So there's definitely some additional areas for research in this area, but that's what we've been working on the Daily Erosion Project recently. That wraps it up with a little bit of time for some questions. I should escape. And I was also going to show you the daily erosion map. So dailyerosion.org/map. And so you can see here we had a little bit of precipitation for the Daily Erosion Project over the last day, because it always brings up your most recent day or the previous day. So March 2nd today, we aren't good enough to know what's exactly happening today as it happens, but that's where we're at. That's a little bit what we can do here. Any questions?
Thank you for the presentation. So I have a couple questions. One generic question. So I'm not very familiar with the crop residue predictions, but what are some general values we can get from knowing the spatial variation of crop residue?
So what are some? Well, so one of the things that things we can know from the spatial variation of crop residue is what I'm kind of hearing the question to be. As for the Daily Erosion Project, it does allow us to estimate the soil erosion losses, because we need to know what residue cover is to estimate soil erosion. One of the things we're interested in, though, is reducing soil erosion. And if you can see differences in residue cover across areas that are driven by, not purely the underlying soils, but especially by cultural practices that farmers are choosing in different areas. And if some of them have definitely lower erosion rates than others, there's probably some indication of need for trying to reduce erosion and reduce nutrient losses. Those are definitely great areas for outreach to try and educate farmers on other ways that they can manage their soils and reduce erosion.
Okay. Thank you very much. And two more questions. How did you validate the regression models? Did you use cross validation or holdout sets? And the other question is that I saw that you took samples from only limited locations in the Iowa. And so basically we happen to transfer these models to other areas of Iowa where we didn't have samples. So how
Right.
are you sure that the model performed well?
Yeah, so we are definitely going outside of our inference space we are doing estimates out, even outside of the state of Iowa. We did use what is it? Leave one out process. So we were doing 80-20 training, but we're with a rotating, we're rotated every set of samples in using the 2015 and 2016 sample data. So we didn't use any of the 2017 sample data for the training validation process when we were doing that. Then we went in with a completely independent, the 2017 validation data for validation, and that's what our results are reported as using that fully independent 2017 data set. But yeah, we're definitely we're expanding our area, our inference space beyond our training data set for sure.
That's why I'm also interested in that, because I'm working on transferability. Precipitate soil fertility properties in like training with one field and then take this model to other fields.
Mm-hmm.
But that's why I asked that how did it perform? Like, was it good?
Yeah, and
also you could know that.
Yeah, what we've done right now is what we're doing right now is bringing our to do some not true validation, but confirming the model is reasonable. We've been looking at various regions, both inside the state and across the outside of the state, to see if we see trends that we are generally know to be true. If you look at the state of Iowa estimates, I'll go back to. If you look at the state of Iowa estimates, the MLRA includes the Missouri River floodplain, the Loess Hills, but we definitely see a tillage difference, and the residue cover numbers are much lower out in the Missouri River floodplain than they are in the Loess Hills. I've been out there a number of times. I know that's the case. Those guys are tilling like crazy on those laser level fields that are flat as a board, and they're trying to dry them out. When you get into the Loess Hills, most of them have conservation plans requiring minimum levels of tillage, and we see much higher residue cover numbers in those areas. So we've been very happy that our model is, outside of the training data set, is predicting the trends that we've observed external to this. So happy so far. We see similar. I've looked at some of the trends in Nebraska as well, where I've got a decent bit of knowledge. I've got aunt and uncle uncle and cousin that farm out in the Panhandle area, so way out in Nebraska. We're doing okay out there as well. I'm happy that with this limiting amount of training data that the model is performing as well as it is out there. We've got some ideas on better ways to train this without having to collect so much training data using some big data techniques, but there's always more research to do.
Together, I really like the presentation.
Thank you.
Could you
Yes,
go to the slide previous to this? The percentage residue coverage, what you measure in the field.
So yes, these are the measure. Yes, these are the ground truth values for residue cover.
And did you try to relate this residue cover with the erosion that you obtain on your measurements?
No, we don't have. We don't really have any good sites for doing that. The best thing we have, what we're doing some other validation work is the strips, the prairie strip sites where we've got our control and our treatment watersheds. And those are really the best things we have for continuous erosion measurements that we're working with. So we're kind of trusting the model, the WEP erosion model, to be good as long as we're giving the WEP erosion model good data.
And the measurement that you have for the daily erosion, the metrics, how are the metrics? I mean, the estimations. did you also, what you obtain in your measurements, then you check in the field to see if what you measure in the model is similar of what the model predicts?
For erosion,
Yeah.
so yeah, that's what you would typically do. We haven't done much actual erosion model validation at this point. As I said, yeah, we're mostly trusting that there's tens of thousands of years of plot data that the WEP erosion model is trained upon, just like the USLE and Russell 2 erosion models were trained upon. So we're trusting the models to be valid and give us reasonable erosion rates as long as we give it accurate estimates of what's happening, what the soil's properties are, what the terrain, what the elevation is, the slope is, and what the management practices are. But we do need to check that, and so we're currently working on that with these prairie strip sites where we do have some small watersheds where we've got measurements of sediment that's departing the bottom of the watershed in these small watersheds. And they're pretty similar, pretty close to what you would consider a WEP hill slope. So the WEP hill slope model that we use should give us pretty decent estimates of what's going on in those areas if the model is performing adequately.
I have kind of a follow-up question about that. I was curious of the same thing, connecting the residue cover to the erosion. And if any studies, because this is in my area, Brian, but if any studies have looked at the quality or thickness of the residue, not just the coverage from like a satellite or imagery system, does the thickness of that matter, or how coarse it is versus finer residue pieces affect ultimately erosion?
Yeah. Boy, and I haven't been reading. You can't read as much of the literature anymore. There's constantly more and more journals. So I don't know if anything more recent, but in the 80s, when they were building the WEP erosion model, they did a number of studies to correlate soil loss with different parameters, and the mass of residue cover is kind of what they determined to be one of your best predictors. But that's then there's a paper in the early 80s that converts mass of residue cover, which is typically often measured, and converts that into an area coverage of residue. So that's what's typically done, is estimating how much mass there was, and then how much area could that residue cover. I don't know how much the thickness, if you can get just a 1/4 inch of residue cover versus a full inch or two of residue cover. I'm guessing there's going to be some improvements in reduced erosion, slowing down that water even more as it gets to the soil surface, and it's going to retain a good bit of moisture in that residue mat, and not even allow it to reach the soil surface, so it can't move anything off. Boy, I don't know. WEP is not responsive, to the full thickness of that mat.
This is Brian Hornbuckle. Can you hear me okay?
Yes, we can.
So I'm super interested in this and looking forward to learning more. I have maybe a difficult question. I'm just trying to learn here, but here's my question. We only see 20 to 30% residue cover and no cover crops on the Gelder farm.
You bet.
Why?
Because I don't make all the decisions on the Gelder farm. So that's a great question. I've answered this. I'll answer this question because I've answered it before. So for the last few years, we did some limited tests of no-till on my parents' farm, and we were never really happy. And we were trying it just on soybeans. Now, soybeans are usually your easier crop to generate good residue cover. We just weren't able to get the stands at emergence that we were hoping for. We weren't getting good closing on the after the planter, so we were losing some stand to that. We tried a couple different 2 or 3 different types of closing wheels on our planter. Weren't able to get that. My dad is interested and still very interested in trying strip till. Boy, strip till, buying a strip till bar, depending on what you look at, a lot of, what was it? $2,000 a row unit. You're talking a $25,000, $30,000 piece of equipment just for the row units, and then you got to get a tillage bar for it. We weren't going to try, and we were also looking at Dad's like, how much? I'm not going to be farming more than 4 or 5 more years. This is when I started farming with him, and he's like, "Do you want to buy that?" I'm probably not going to become a full-time farmer myself. So it's the conundrum a lot of farmers face when they're switching practice. When we encourage them to switch practices, hey, you can do this and reduce your erosion. Sure, yeah, that's great. Who's going to come and train me to run the new equipment? I need to set up my planter differently than I've been doing it for the last 30 years. I need to go buy a new planter. New planters, you get 24 rows. They're well over $100,000 for 24-row planters now. So there's a lot of problems there. We mentioned cover crops. We haven't figured out. We like to do manure, and there's potentially some ways you could work manure into cover crops, but that's another complication of, we can't interseed it, before harvest, because we're going to go out and put manure on all of our soybean ground, because we're going to put that on for fertilizer for the next year, and that would wipe out your cover crops if you put it on your soybeans. So we got some practical reasons why we haven't done that. We still keep talking about it. Our tenant farmer that we have now he's interested in doing some strip till, but yeah, as I said, it's learning a new system of management while you're during the crunch time planting season, when you want to get out there and plant as many acres as you can, as fast as you can, is difficult.
So with that, are we? It's like we're kind of assuming that more residue cover means less erosion. So if the Gelder farm has a low amount of residue, does the Gelder farm have some of the highest rates of erosion?
Well, if you're looking around the area, we are not really. Look at the Gelder farm. So we got the Gelder farm here. Our estimated residue cover is a little bit lower. I would say a little bit lower than our neighbors to the north. But our actual residue cover numbers are not really any different than our neighbors to the north. I think those are a little bit soil differences. His depressional area is right here. He turned it into a wetland reserve for government programs. And so he doesn't farm his lowest portions of his field up there. I don't think we're pretty run of the mill for what we do. In the area we're at, we're very run of the mill for our residue cover management practices.
Sorry, I was trying to see.
Since we're in the Des Moines lobe, we're pretty low, just because we don't have, a 10% slope is exceedingly rare. It may cover 1/10 of an acre on in our fields. We get, the top of the hill, maybe you get to some 10% stuff, but boy, you're off a 10% slopes are really fast. Most of it's, 1, 2, 3%, 4% slopes.
That's what I was trying to draw attention to. I don't know if you want to pull up on the Daily Erosion Project, but the statewide annual, or say last year or whatever.
Oh, yeah.
We can look at the map for where there's lack of residue cover on Des Moines Road, but that doesn't necessarily mean that Des Moines Road has an erosion problem. Relatively compared to say the rest of the state.
Yeah. Yeah, and that's one thing. It's hard to, we're thinking we've discussed some different ways to be able to set up the Daily Erosion Project and normalize it, and try and account for some of these differences, the differences in erodibility of your soils and slopes of your soils, what crops you're growing. Evidently, we're on precip, so that's why we'll see something a little more interesting if we look at. So here's soil detachment for the year 2021. Des Moines lobe, you can pretty much see right where it's at. Nice low slopes in that area. We don't have very high erosion rates. We're typically in the, it also didn't rain that much during the erosive parts of the year, and we got a lot more rainfall in the erosive parts of the year down in southwest and south central Iowa. So, is that because they're bad farmers down there? No, it's definitely not. They've been definitely dealt a different hand of weather this year, and their soils are much more sloping than ours are. How do you give credit for being dealt those hands versus other hands, as you'd say in poker, to try and normalize those things? We don't have a great way of doing that. We brainstorm about it every once in a while, but haven't come up with any great solutions for that.
Well, there's no questions online.
Well, Brian actually, Hornbuckle asked one, so we did get one out.
When you mentioned the concentrated flow, how do you determine when it starts the concentrated flow?
So we can spend we got a whole other research paper on this. Luckily, we had a visiting scientist, Chunmei Wang, who came here from China just before COVID really shut everything down. So some of you may have met her. What she did, don't really have a great graphic to show it, but she validated our approach of using what we call grid order, where we look at, here, if you've done stream order calculations, where you say the first stream where you initiate, that's a stream order 1, and then 2 1s would come together and you get a 2, 2 2s to come together, you get a 3. That's the stream order concept, often used in hydrology. Wildlife fisheries folks like to use it for analyzing their data on headwater streams and other streams. We used a similar approach called the grid order approach, where you, instead of starting at designated streams, you start at flow initiation, flow accumulation equals 0 in a GIS analysis, and start from there as your first order cells, and then increase your accumulation from there. Once you get to grid order 4, I think is what our paper found, I'm trying to remember the exact number, because it also varies based on resolution of the DEM you're using. But when we got to grid order 4 is when we start to see gullies appearing in the landscape. So she went out and looked at 10 Huck 12 watersheds across the state, and in some of these small subcatchments, she mapped every gully initiation spot she saw, and then we looked at what values, a few different terrain indices, and said which values are critical or threshold values. And there's other things like the stream power index, wetness index, that are commonly used to indicate some erosivity, stream power. Those metrics, or even just simple flow accumulation as metrics to say when channelization starts, those metrics perform well in individual watersheds when they're calibrated, but they don't perform well across the whole state. And our metric of grid order actually doesn't perform as well on a per watershed calibration basis, but it performs better across the entire state than any of the other metrics that we're using. We just threw it, when we started the Daily Erosion Project, we just threw that in and says, that sounds good and it looks really good based on our eyeballs, but we didn't have anything to really back it up. so they allowed us to publish it before before that. And last year we finally got out an article to validate the approach we've been using for the last few years before that. But that was good to see that it's holding up. We're expanding that work now with Nebraska, Iowa, Missouri, and Kansas through some NRCS funds to look at this grid order approach across those 4 states and look at its ability to predict gully erosion and try and help the NRCS target different areas where they think gullies are likely to form.
Dr. Gelder, is the DTAP code connected to the website? So automatically calculates the maps and then put out in the website, or how does it work?
The DTAP or the DEP? Yeah. Daryl has the code fully automated. So unless something blows up, he doesn't have to, and he's also got it automated. So he's got a program, if something blows up, his computers email him and say, you might want to take a look at this. But yeah, he has everything, it starts to check the radar, it's our biggest thing is the radar data, the rainfall data. And so there's a little bit of lag before they can push that radar data out. So that's why it starts around 1:30 to check to see if the data is available. They do some quality control checking at the end of National Weather Service before we use it. So it starts checking around there. Sometimes it takes a little bit longer than its 1:30 start time for that data to become available. Once it's available, it starts spinning up all the different routines. He's got to change the climate files every day to incorporate that most recent weather data. Most of the other stuff doesn't get changed except for every year. We upgrade the residue cover now and management.
So if you had to guess, like the percentage of the manual work involved in this project, what would you say?
Well, how would you try and evaluate that? The computers can do these calculations, these numeric calculations insanely faster than we can. How do you weight a computer's time spent on this versus a human's time spent on this? On the amount of time it'd take a human to do a